Good afternoon. My name is Joe Warner, and today I'll be going over section 4.8, El L'Hopital's rule. In this video, I'll be going over a few important limit problems that will involve different types of indeterminate forms. We'll cover how to identify them and apply right strategies such as El L'Hopital's rule or logarithmic manipulation. Let's get started. So before I go forward, I will show El Hopital's rule throughout the semester. This was definitely by far, for whatever reason, one of the easier rules to catch on to. I don't know why, um, but yeah, I will go into the examples now. So our first example that we'll go over. So it's stating as x approaches 1, both the numerator and the denominator approach 0. So this is an indeterminate form, type 0 over 0. That means L'Hopital's rule can be applied. So we'll take the derivative of 1 over x right here, and then the derivative of x minus 1. Oh, my apologies. We'll take the derivative of ln x, which is 1 over x. And then we'll take the derivative of x minus 1, which ends up just being 1. The limit then becomes limit 1 divided by x over 1. And then that's going to end up equaling 1 over 1 or 1 over x. And then you're going to apply your x into the x. It's going to be 1 over 1, which is going to end up giving you 1 for our final answer. Now, our next example, we're going to be changing it to a fraction. So here we're asked to evaluate x approaching 0 from the positive side of x log x. So log approaching negative 0. So as x approaches 0 from the positive side and x approaches 0, and log x approaches negative infinity, this is a form of indeterminate, and it is 0 times negative infinity. So that's the indeterminate form. So to rewrite it, we're going to do x log x equals ln x over 1 divided by x. Now it's a rule of negative infinity over positive infinity, as we see right here. So now that officially means we could use L'Hopital's rule. And then our derivatives are going to be our numerator right here, which is 1 over x. And then our derivative of our denominator ends up being, minus 1 over x squared. Now, our after we apply that, our limit's going to become 1 over x, or 1 divided by x over negative 1 divided by x squared. That's going to equal limit negative x, which essentially, when you apply your x, which is 0, your final answer is just going to equal 0. On to the next example. The next one is going to be combined fractions or factoring out an x. I picked one with ex in it because I've always talked to a professor or Sophia about these always confuse me for whatever reason. But yeah, I went through the pain of going through one because once you do them, you find out that they're actually one of the easier ones. So this specific example asks us to evaluate the limit as x approaches infinity of e of x minus e. Both e of x and x approach infinity, so this is an indeterminate form of infinity minus infinity. But since the exponential functions grow faster than the polynomials, we know that e of x minus x is going to equal or approach infinity. So the exponential ends up just being infinity. So your final answer is going to end up being infinity anyway. So yeah, I feel like I do more explaining of what the answer is instead of the actual work that you actually have to do for some of the EX problems. One of our final examples, take the log of both sides. So this example involves the limit of sine of x to the power of x as x approaches 0. As x approaches 0, sine x approaches 0, and x approaches 0. So this is a indeterminate form of 0 to the power of 0. So to evaluate it, we'll do y equals sine of x to the power of x, and then we'll take the natural log of both sides, and then so ln y equals x ln sine of x. As x approaches 0 and sine x equals x, we can approximate this is where did I put it? Is x ln x, which is right here technically, or right here, x ln x. And then we have we already found that the limit of x ln x was 0. And then ln y approaches ln y approaches 0, which is going to mean that y approaches e to the 0, and then once we apply our x's and y's, we're going to end up left with our final answer being 1. And yeah, so that wraps up the review of the limit problems. Each one used a different strategy depending on the indeterminate form of L'Hopital's rule, rewriting as a function, comparing growth rates, or taking logarithmics. I hope this clarified how to approach these kind of limits for anyone that watches it, or you know the professor enjoys it. So thanks for watching.